everyone, and welcome to part 3 of this live workshop series where we are motion activating all the things with a PIR sensor and an Arduino. Today, we are going to tackle DC motors. So by the end, you're going to know how to wire it up along with the PIR sensor. And we're going to go through a couple code examples that you can then take, modify to your whim for your own projects. Let's start with our PIR sensor. And for that, don ye eyeballs, everybody. If you got mature eyes, go ahead and get them set up. We have our time delay on the left. If you turn it clockwise, it increases the time that this remains high. I have it set to all the way low, so it's like 3-ish seconds. On the right, we have our sensitivity. How far does it sense? Anywhere between 3 and 7 meters. I have it short range at about 3 meters because, I'm right here. Like, sense me. We have our jumper or trigger mode selector here, and it's in the L position, which means single trigger mode. So that way, a motion happens and I have this time delay set to about 3 seconds. That means it's locked out for 3 seconds and then it resets. And the other position is just removing this jumper and jumping it over to this pin. That's the H position, meaning repeat trigger. So if I had this set, say, for 2 minutes, I walk by, the 2-minute countdown begins. I walk by again, the 2-minute counter restarts and it keeps restarting. Definitely a better application of the trigger jumper in the H position if you're using this for a room light or a bathroom light where you don't want it to keep turning off. So we're going to leave it in the single trigger mode. That way we can trigger things kind of quickly. Then we have our pins. So VCC on the right, our signal pin in the middle. This sends the signal, whether high or low, to our Arduino, and then ground on the left. And if you can't remember, you can cheat. I do this all the time. You pop off its noggin. That's why all the electronics take off running. They're like, oh, she's taking things apart. Run! Save yourselves! This guy's like, it's too late for me. We have VCC out and ground right there. The first thing I'm going to do is basically connect our positive rail to the 5-volt pin of the Arduino. And then I'm going to tap this little guy in here so he can be all happy. And he only requires 5 volts, so it's a really easy hookup. Our signal wire, I think we've been using pin number 12 of the Arduino, so we're going to stick with that. It's been our lucky pin. I have a positive coming here, but I have no negative, so I should probably hook that up. I'm going to put this in the ground right here, which is right close to the 5 volts. They can be like little buds right there. They're BFFs. So we have our power and ground hooked up. We have our PIR sensor here hooked up. Now let's hook up the motor. Unfortunately, it's not a good idea to hook up your DC motor, no matter how small and no matter how little current you think it draws, directly to the Arduino. Because on a best case scenario, you will fry whatever pin you're using. Worst case scenario, you will brickify your board there. So you can use it as some outdoor decor, a nice paperweight. Instead, we need an intermediary, and this is our motor driver. And it's got a bunch of connections. We're going to run through them here real quick, but it's very important to pick the motor driver that contains the voltage and amp requirements to run your motor. So this one is a pretty beefy one to run a windshield wiper motor. I know a lot of you prop enthusiasts building homemade props. This is like the go-to motor. They're super cheap. They have a lot of torque. So that's why I'm using this as our example. No! I have him hooked here into his slot. This can control 2 motors, so I can certainly connect another one there. And you can see the black for ground. Yellow is for our high-speed wire. This is a 5-wire motor. And if you need to figure out what your wires do on your windshield wiper motor, I got a whole video for that too. So the orientation of your wires here largely doesn't matter. In one configuration, this will turn either clockwise or counterclockwise. If you flip it, then the turnage will change as well accordingly. It needs its own power, and that's where I have this hookup right here. I have this kind of like brick style 12-volt, 8-amp power supply. To run a motor like this, you need a minimum of 5 amps, and you want to match up the volts exactly to your scenario. And what this module does is take power from this separate power supply, shoots it down, and powers your motor. It has nothing to do with the connections we're going to be making to the Arduino. It separates the power, thus not harming this Arduino. So I don't know, he might walk out of here today. We'll see. You can see 2 vertical rows of pins. This vertical row is for the other motor slot that we don't have a motor hooked up into. So we're going to concentrate on this first vertical row. We have our 5 volt. So the motor needs power. We took care of that. But it turns out this board needs power too. And it's not using this power. It needs its own kind of power. Well, the Arduino can also provide 5 volts. So why don't we tap him in here to the breadboard where we can suck the 5 volts out of here into our little motor module there. So I have a jumper here and he's got a female end and a male end. So prepare the power suckage. There we go. And I'm actually going to move maybe these guys up here. Make sure not to reverse the polarity there. And he's gonna go right there, thus taking power and powering his own self. So the next one is called ENA. Now this is a speed pin. How fast do you want your motor to turn? Now if you want to control speed on your motor, it's important to pick a pin on the Arduino that has the squiggly, the pulse width modulation pin. And I'm gonna put him on 6. Hopefully some of you guys are remembering these pins. Next 2 are called in1 and in2. Those basically control the direction of your motor. So if you send 5 volts to in1, it'll turn one direction. And of course, that also has to do with how this is wired. So we're going to figure this out in the code. And in2 makes it turn the other direction. So those do not have to be PWM pins. They can be regular old pins. Let's go 7 and 8. So in1 is in 7. And in2, let's put that into 8. Oh, and this has one more little pin left, and that is our ground, because it is super important that every component that you hook up, the PIR sensor, the motor or servo, whatever it is you're using, they all have to share a common ground with the Arduino. So they're all kind of talking to each other. So that's one of the first things to check. If you get to your code and something's not working, make sure you have that common ground. Here we have our sketch. And the first thing I want to do is, before we get started, let's just make sure that PIR sensor works. First things first, let's set up our pins as variables. So we have the PIR pin, and we connected that to pin 12. There's a lot of different ways that you can set up your pins up here as variables. I'm using int for integer. It's kind of a nice beginner-friendly way to do it. So the first thing we want to set up after our pin is a variable to track the motion status. Is the PIR sensor high or is it low? So we need a way to know. We're going to start it at 0, which is the same thing as low. And then I'm going to set up kind of a label for us to track the state of the PIR sensor. So the motion status will constantly read that pin. Is it high? Is it low? And it's constantly updating. But we just want to know when the state changes. We don't need to know every millisecond whether it's high or low. Just tell me when it goes low and just tell me when it goes high. So next, why don't we set up our pin modes? So we're going to forget the motor for now. We'll come back to that. And we want to set up our PIR pin or PIR pin as in input, because it is going to be receiving information. Is the pin high or low? Has motion happened? And probably before this, which is the step I always skip, and it's not a good idea to do so, but sometimes I'm flying through this type of stuff. So is the serial.begin. And that allows us to use our serial monitor to monitor whether or not this is high or low. For the setup, I like to add a delay before anything gets started. Your PIR sensor needs to calibrate, and this takes about 30 to 60 seconds. So if you have it hooked up to a motor or like a silly string shooter, the way we had at one point, it could just start going off. So you want to make sure that we already set the state to low, and we're starting with a motion status of low. and just keep it that way for 30 to 60 seconds. Now, because we want to like go through these experiments rather quickly here, I'm going to put 2 seconds as a placeholder, and hopefully that'll help you guys remember to put some kind of delay here. So now we are at the loop, and let's go ahead, and first thing we want to do, we want to read the pin. Is motion going on or is it not? So for the motion status, we want to put either a high or a low inside this variable. So we're going to do that by digital reading the PIR pin. What do we do with that information? So whether it is high or low, it's going to store that value in here. So let's do something with that info. And so if the motion status is equal to high, not equal high, but is equal to high, what do we want to happen? So right now, our PIR state is toggled to low. So let's nest a if statement, if you will. So if the PIR state or the PIR state is equal to low, what do we want to happen? And it is equal to low because we set it equal to low right here. So right off the bat, if motion happens, it's going to jump in this if statement right here. So if the motion status is high, that signal coming from the pin is high, jump down here. Oh, and this happens to be true. So let's execute the code within these brackets now. So we want to go ahead and print serial print the fact that motion has been detected. All right. And then we want to flip our PIR state to high. So this is our own label that we're using to toggle it high or low. It's tied to what's going on with the pin. So as soon as the pin reads high, our label toggles to high as well. But it's a way to toggle it one time versus like, hey, I'm still reading high. I'm still reading high. You're like, okay, I got it. It's got to tell me once. Once it takes another reading, what if it's not high anymore? So, or else, if it's not high, what do we want to happen? Well, first things first, let's address our PIR little label situation here. So if the PIR state is equal to high, which it would be because the sensor was just high. So this is going to be high. And so in that case, we want to serial print the fact that motion has ended. Oh, and I got way too many quotation marks going on there. Let's get rid of them. And we also want to toggle our PIR state back to low. So that way it's ready for another round. So what's going to happen, it's going to go right back up here, take another reading. And if it's still low, there's no motion, it's going to jump down here and it's going to keep our PIR state toggled low. And then if it goes up and it reads that it is high, then it's going to jump into this if statement rather than going to down here. Oh, this actually needs to be like this. Oh, now we have missing brackets. I'm going to pop open the serial monitor and let's see if we have our motion sensor working and that I wired it up correctly. Nice. So our PIR sensor is working. I say that we hook up our motor. So we have our ENA pin, and you can call it anything you want. Remember, the ENA pin is your speed pin. So you can call it speed pin if you want. Sometimes I like to just stick with what's labeled on the component, so that way it makes it easier for me to go find it. And so I believe that was 6. Yes, that was pin 6. The in 1 pin then was hooked up to 7 because I remember we went in order. The in 2 pin then was hooked up to 8. So I think that's all the pins that we need. And then here, we probably need a couple more pin modes because unlike the PIR sensor where we're grabbing information from it, we are going to be outputting information to all those pins on the motor to tell it to do stuff. We're going to boss it around a little bit. So the ENA pin is going to be an output. And then the in1 pin is also going to be an output. And then what else do we have here? The in2 pin as well an output. All right, so I think that's it. We're going to leave our delay as our little placeholder there for the PIR sensor to calibrate. And the rest works much the same. So I say, let's just get this thing to move, turn in a direction. So as we recall from the last time, we can either put code to activate components here. This is our option 1. Or we can put code to activate components here, which is our option 2. So let's go with option 1 first, and then we'll explore option 2. So I'm going to get rid of that. If the signal coming from the pin is high, what do we want to do? We want to digital write our in1 pin high. So let's turn in1 high and turn it in that direction. So if we're going to do in1 pin high, it's good measure to then be very specific and say that in2 pin then is going to be low. You can't turn the motor in both directions at the same time. With a lot of motor modules, that means brake. It'll turn on the brake. So it's always good to specify one high and one low. You can get away with not, but sometimes there is some confusion. So now we put the car in drive, but nobody's stepping on the gas. So now we got to step on that gas, and we are going to do that by analog writing that speed pin. So that was the ENA pin. And here you don't go high or low because it's not either like running full speed or not running at all. Much like LEDs, you want to pick a value anywhere from 0 to 255. 255 obviously meaning lead foot pedal to the metal. So you can pretty much guess which speed I am going to pick right there. Heck yeah, pedal to the metal, people. And if there is no motion, we want the motor to stop. And same thing here. We can put the code for option 1 for putting our code or option 2 for putting our code. And you'll find that I like option 2 much better for most applications than option 1. But because we did option 1 up top, let's do option 1 here and keep everything kind of like nice. So we're going to digital write the in2 or the in1 pin low because we had it high here. So we need to turn power to that pin off. And also we want to do the same to in2. So that way the car is in neutral. It's not going anywhere. And we are doing all the misspellings today. It's like we're collecting them all in this stream. There we go. So we've stopped everything. Now, do we need to put a speed here? I could put 255, but the car's in neutral. It's just going to sit there stopped. It's not going to do anything. So we don't really need to put a speed here. All right, here we go. Let's see what happens. Oh, can someone tell me why the motor is not turning? Yeah, maybe I just learned this last week. Like there is still no Wi-Fi power. So that's a thing that I keep thinking has been invented, but it has not. Here we go. All right. And you can see it moves for just as long that we have that time delay set. All right. And what if we turn up the time delay? Now it's going to keep going. I put it into the time delay of doom where it's going to take forever to turn off. Let's do that. There we go. Let's now try and make sure that we have the opposite direction also configured correctly. So here, if the motion goes high, I'm going to swap and do low here, and I'm going to swap and do high here. So theoretically, it's going to spin in the opposite direction at full speed, people. Yeah. Even touching it, it's like, don't touch me. But yes, guys, look, it's turning now the opposite direction. Next, before you start any animation with a motor, is to find out how low can you take the speed before the motor just stops working. One would assume that a speed of 0 means no movement, which is true. And 1, 2, 3, 4, 10, the motor starts to move really, really slowly. So why don't we take it down to 10 and see what happens? Can you guys hear that? It makes a really kind of high-pitched. So why is it not turning? The motor will always get 12 volts. It just depends on how many times it's getting 12 volts per time interval. So if you don't choose 255 and you choose a lower number, say halfway, then this will only pulse 12 volts half of the time. So that means it's going to travel half as fast. But it gets to a point where it's pulsing so very little times per time interval that it's not even enough to turn this thing. So you'll write all this code, orchestrate all this beautiful movement, and find out that, oh, my motor doesn't turn below 70. And each motor is different. So let's find out what our bottom is. So if we remember correctly, way back when we were working with this motor, I think it was like 70. I think 70 was enough to get it moving. Oh, it's so slow. Yep. You see how slow that is? And we have it set to the smallest time delay. So the objective is to find a number where it reliably works. Say you only want to turn in that one direction at full speed for maybe a short amount of time. Say, half a second. So you would think that the motor's going to turn for half a second, stop, and then take another reading. So let's see what happens. Seems a little long for half a second because remember, this is about 3 seconds. Because we have our code block in option 1, this keeps taking so many readings per second that it's like, oh, it's still high, keep it turning. But say we want to only turn it for half a second. What happens when I put the time delay up? It will turn it in the direction for half a second and immediately be reading again and keep turning it. So each half a second turn is all being added together in creating this continuous turn situation. So instead of putting all this business where the pin is constantly reading high and it's based on the absolute current state right now of the pin, let's take this and we're going to cut it. And this is where the problems start when you start copying and pasting. And we're going to put it in this if statement here, which was our option 2. And my indentations aren't quite right, but we're just kind of copy and pasting here real quick. So now what should happen is we're going to get a high reading from the PIR pin once I wave my hand on it. And because we have just uploaded the code, the PIR state is set to low. So this is going to be true as well. So it's going to say motion detected because the PIR pin is reading high. So first thing we're going to do, let's flip this switch on to high for our PIR state label. And once that happens, this is going to execute. And it won't execute again until it reads low, and then it takes another reading for high. So here we're going to go digital write the in one pin low and digital write. I suppose you can only digital write the in 2 pin. There we go. So let's see what happens now. So here it is all the way down, and you can see how it turns much quicker now. So even when we had this set all the way down, short time delay, it was still going beyond the half a second. So let's turn this up just a little bit, not like the way I've been doing it. Yeah, so now no matter what time delay I'm setting, that thing is only turning exactly as we told it to. It's one of the big advantages of using option 2 over option 1. If you're trying to orchestrate something specific, the option 2 location is the better one to go. And you'll notice that we forgot to put this in option 2. For good measure, this should go down here as well. So both are in the option 2 position. You walk into a haunted house, a spider that rolls down from the ceiling, scares you, and then rolls back up. So how would we do that? Here, let's make him roll. And I'm going to turn him back the other direction. And we're going to make him go that direction for like 2 seconds, right? And then we're going to stop the motor. The spider has come from the ceiling. We want to stop the motor and we want to pause it there for how long? It's going to like scare people and stuff like that. So we'll pause him for like 3 seconds. Obviously, you need more than 3 seconds, but for demo purposes. Then we want to retract him back into the ceiling. So he's going to go back into the ceiling and we're going to reverse what we had. So in pin was high. Now it's going to go low. And the in 2 pin now is going to go high. And we want him to retract also at full speed. And so the ENA pin, our speed pin, we're going to pedal to the metal, that whole thing. All right. And how long do we want him to take to get back? Maybe the same amount of time, maybe like 2 seconds, something like that. And then maybe we want to stop it, stop the motor. So I'm just going to copy and paste. There we go. And then we can else the motor is stopped in the option 2 position. So no motion, the spider stays tucked up, hidden, ready to get you. So let me go ahead and upload this. It stops. It's scaring everybody. Oh, and then it rotates back. All right. And so it does it 1 time, no matter how you have your time delay set. So what's left to do? Well, why not accelerate the motor? Maybe you want your zombie to start slow and then really go after the person. And when you walk through haunted houses, a lot of times you see things reset behind you. Sometimes a jerky motion back and forth like that can start to wear out your linkages. So sometimes it's best for the motor and your linkages to start and just kind of ramp up that speed and then ramp the speed back down. We're going to use our option 2 area. And if motion is detected, what do we want to happen? Well, first we need to pick a direction. So this thing is either going to be in drive or in reverse. So let's digital write the in 1 pin high. That's kind of what we've been sticking with. And then the other pin low. And how fast? Oh, we can't put a speed, a number. We will have to create a variable. So let's go back up here and set up some kind of variable. So we'll call it M speed, motor speed. We're going to start at 0. And this is another good thing to do in addition to zeroing out any sensors that you have, any motors or servos. It's good to kind of zero it out, or as a servo, put it in the starting position that you want before anything happens. Let's set up a for loop, which is a great way to iterate through a whole bunch of numbers one by one. So for, we called it M speed. Where do we want this speed to start if it senses motion? We want it to start at 70 because remember, up at the top, we set it to 0. When this sketch starts, it's going to be stopped until it senses motion. Now, if we did 0 here, it's going to go 0, 1, 2, 3 until it gets to 70. So that motor is going to be stopped for quite some time. So M speed, we're going to start it at 70. And so long as the M speed is less than or equal to 255, which is full speed, what do we want to happen? Well, we want to take that M speed and we want to add 5 to it. Yeah, let's increment by 5 versus 1. So we're not sitting here like 1 or 70, 71, 72. It'll go 70, 75. 80, 85, and that'll give us a nice smooth acceleration. Analog write, and we're going to write to the speed pin whatever the motor speed happens to be. How fast do we want the jumps to happen? Let's start it at 250 and then we can kind of finesse it, from there. Our motor is not going at 255. And so we want to keep it at 255 for the duration of the high. So let's keep this going at 255. Or no, let's keep it going at the M speed, which is going to be 255. What happens if the motion sensor now doesn't sense motion? This thing is going at full speed. So if it stops sensing motion the way we had it before, it's just going to stop like that. Why don't we decelerate it down a little bit? Why don't we reverse the motor too? So let's go digital right. Now I'm adding all kinds of fanciness. So we had in one was high here. Let's add in one pin low here. And digital right, our in two pin high. So we're reversing direction. It is now in reverse, but we got to step on that gas. But we will do so slowly as if for a nice deceleration. So again, with our for loop, we are going to start our M speed because from when it was high, it was 255. So we're going to start it at 255. And so long as this M speed is greater than or equal to, not 0, let's do 50. Because 50, I don't think that motor will be turning. The motor speed, we want to subtract 5 at a time. So again, we want to analog write the ENA pin by the motor speed. And how fast do we want to decelerate? I'm thinking pretty fast. We want to retract our thing and get it ready for the next scare. So why don't we do 50 milliseconds per decreased interval? Because I set a speed here below what the thing can even do, it's probably good. It's going to stop on its own. But if you want for good measure, once it reaches 50, you can just turn them off by going digital right. The in one pin low and digital right the in two pin low. Because if you remember, even though it's not turning at 50, it makes that annoying sound. So we don't want any of that if we just turn it off. Okay, here it goes. It's accelerating so slowly. This is the most boring zombie. Now it's decelerating because it doesn't sense motion. He came out you, first of all, like Grandpa Zombie, hold on, kids, get off my lawn with his cane. That was the slowest acceleration I've ever seen. So instead, why don't we make him accelerate a little bit faster? We'll change this to 150. Instead of that, why don't we put in just 255? Let's put in a hard number here. And we have the slowest time delay. Here in the code, after it reaches 255, I'm just going to hold it for 255 so long as our PIR state is toggled to high. If we only want it now to turn it for a select amount of time, let's say we want to turn it for 3 seconds. And that's not 3 seconds, that is 3 seconds. Let's see what happens. It's accelerating. Grandpa Zombie's coming for you. Get off his lawn. Okay, it's holding it, and then it's decelerating. We went through a couple code examples, so hopefully you guys can mix and match a lot of the code I did, build upon it, expand upon it, and heck, then share it with us. These are shot live. I will probably come up with more cool code ideas. So that's why I always write a detailed tutorial, which the link will be in the description. It's going to have wiring diagrams. So if you saw this RAS nest and you were like, yeah, I don't know if I can follow that, I'll have a nice purdied up wiring diagram for you guys, along with all the code examples that we went through. So you can copy and paste, modify, and do what you will with it. Next, we will be toggling MP3 players, because what is the thing missing from the prop? We got its eyes, we got servos for its arms and perhaps a jaw. We have motors for it to come in and out at you. Well, it needs to make a sound because silent props are not as scary. So it's got to like growl or get off my lawn if it's our old grandpa zombie. So we are going to be tying an MP3 player to our Arduino and motion activated. I had a blast. I hope you guys did too. And I invite you to join our community. We get together via Zoom. We also shoot these live. You can join all of these live workshops, chat in real time, code along with me, wire along with me. So I invite you to join. Link for that is below as well. Guys, have a great spooktacular night. Bye.